Okay, let's review quickly what we did at the end of the previous class. So I introduced the notion of stability. So as a quick review, a system is stable when for any input that is bounded, the output is bounded. Okay? So that's stability, and you have to prove it for all inputs. For all inputs that is bounded, you have to prove that the output is also bounded. Now, to prove that the system is not stable, what should you do? What should you do to prove that the system is not stable? What? That it's not stable, that it's not bounded. Okay, but what is the precise procedure to prove the system is not stable?
So we give one counterexample.
Okay, so this counterexample should do what?
The input will be bounded.
Yes.
And the output won't be bounded.
Right. Right. So you want one example of input that is bounded that gives you an output that is not bounded. All right? Because this morning I heard all sorts of things like any input that gives something not bounded. All right. All right. So we are going to cover more examples today, and more difficult. But let's start with an easy one. Example 3. S of x of n equals nx of n. Okay, how many of you vote that this is a stable system? And how many of you vote this is not stable? Only? Participation is so low. Let's recount. How many of you vote this is stable? How many of you vote this is not stable? Oh, that was easy. That was easy. Look, take x of n equals 1. Is that a bounded input? So you remember the notation, what that means? All right, this is constant, n equals 1, and is bounded. All right, so what is y of n? Yes? So is that bounded? So wasn't that easy? Wasn't that easy? So, not stable. I'm surprised that usually the afternoon class is better than the morning class. But on this example, you are way like that. But examples are going to be harder and harder, sorry to say that. S of x of n equals y of n such that y of n, two cases, sum of x of k going from 0 to n, when for n non-negative and 0 for n negative. I give you a little more time. It's a little harder. before you vote? Okay, let's vote. How many of you vote this is stable? How many of you vote this is not stable? So, if you say not stable, so can you tell me why? Yeah? All right, all right, all right. This is why I like to include last minute, last second voting. All right, so those who said no, you said no. Those who said no, why did you say not stable? You know what? The same example is going to help. Take x of n equals 1. Can you tell me what is going to be y of n? I mean, obviously, it's going to be 0 for n negative because, right, you don't have choice. So now you tell me the other one. Like that? 2? But that is bounded. That sequence is 1. Almost. Yes. You have to add up. So when you take this as input, you have to add up once. How many times? N plus 1 times. From 0 to n, you have n plus 1 numbers. You know that? Okay. Is that bounded? All right, let's try this one. Oops, sorry, mistake. So S of x of n equals y of n such that y of n is, so still 0, no, okay. So this is when x of n is 0, I take 0, and when x of n is different from 0, I take this one. All right. Don't you think this class is fun because it's like a game? You know, like a TV game. You have to find, you have to say yes or no. All right, let's vote. How many of you vote this is stable? How many of you say this is not stable? Are you sure you? Okay, we always want some losers, right? We always want some losers. I like this class.
Yeah, seriously.
So I tried to discourage him, but he was too confident. He was too confident. Look. What is the problem with this? The problem with this is when x of n is too close to 0. You agree? You are getting problems when x of n is too close to 0. Right? Right? When x of n is too close to 0, this becomes too big. I agree, but it may not be bounded. You're going to see what I want to say here. Okay, fine. Take this is well-defined sequence. Is it bounded? Are you sure?
Yes.
Can you give me a value for A? No, A, value for A. The bound. The bound. Yes, 1, because n plus 1 is larger than 1, so this is less than 1. So obviously it is bounded. More than obviously. What is y of n in this case? No, I want something explicit. X of n is like that, so you give me can this be equal to 1, to 0? No. So we always, in this case, right? So you always have 1 over x of n, which is this. Is this bounded? Right? So not stable. So what was the idea? The idea is that, all right, x of n is allowed to be is bounded, right? The problem is when x of n tends to 0. Can it tend to 0? Yeah, a bounded sequence is allowed to tend to 0. So the problem is that if x of n tends to 0, then y of n tends to plus infinity. So now you don't get a number, you get plus infinity. I mean, I told you the examples become harder and harder. So the last one is the most difficult one. All right, so this one is the hardest. This one is the hardest. Actually, this class, it looks like I'm giving you puzzles more than engineering stuff, right? But I think it's more fun. No? It's more like I see that as a game, playing with pure logic. Don't you think it's more interesting, more fun? Yeah, I'm giving you more time. Okay, let's vote. Let's vote. How many of you vote this is stable? How many of you vote this is not stable?
Eight.
Yeah, but okay. The goal is not to get the right answer, it's really to understand exactly why. Okay? So, this time I'm going to make a proof which is complete. Okay? So take x of n bounded. So there exists a such that x of n less than a for all n. Okay, I'm just writing the definition of bounded, right? Now, so we want to find y of n. There are two cases. Okay, so what is so there are two cases. Either you are in this case or that case. All right. So that case is no worry. 0 doesn't going to hurt you. So so case 1. Suppose that x of n is greater than n squared. But then n squared has to be less than a, because x of n is less than a, right? So n itself cannot be any number. It has to be less than square root of a. So y of n obviously, which is in this case n cubed, will have to be less than square a cubed. Case 2, y of n is 0. So for any n, y of n is less than this. Done. Bounded. S is stable. Okay, that was the last example. Now we are going to move to theorem. Oh, helicopter 2. We had helicopter 1 last time. What was that? Helicopter 1 is something that you want to take when it presents itself. Yeah, right, yeah, you need the system to be LTI, but you forgot what is the question. The question is, helicopter 1 deals with the question of causality. So causality can be checked directly by looking at the impulse response, by checking that all values at negative n are 0. You have a same issue for stability. to check stability when the system is LTI, there's also a helicopter, another one, not the same. Don't take the wrong helicopter. Otherwise, you don't get home. You get somewhere else, right? Helicopter 2 is when for stability. So L, okay. Let S be LTI of impulse response G of n. Then, to determine stability of S, there's a direct way to do it. Then, S is stable if and only if. So there's going to be a way to state stability by looking at G of n, and that test is harder than for causality. You have to perform the summation of absolute value of G of n. Actually, I should say magnitude, because it also works for complex sequences. So S will be stable if and only if this converges, this summation converges. So you know what that means, converging. Okay, it has a limit. In fact, if it has a limit, this is equal to the limit. This is the sum. This is the limit. All right. So helicopter 2 states this, but I'm going to show you why this is true. So, like for helicopter 1, you want to write down the properties of LTI system. Remember that by theorem 1, S is LTI. Since S is LTI of impulse response G of n, then when you look at the response to X of n, then you get the convolution between X and G. I'm writing this in this order because of commutativity. So this means that for each n, Y of n is the sum of G of k, X of n minus k. All right, so that we know this is true. So now I'm going to start the proof. And remember, the proof is in two parts. The easy implication is the backward implication. So let's start with the backward implication. So what do? We assume. So assume these converge. Okay, let's assume this. Let's call B the limit. Let's call B the limit. It's a finite number. So let's prove that S is stable. So to prove that S is stable, take any input. Take X of n bounded. As usual. So again, this means that there exists a positive such that X of n is less than a for all n. For all n. All right. All right. Now we are going to evaluate Y of n and see if it's bounded. Okay. Now Y of n is equal to this. Therefore, its absolute value is the absolute value of this. So far, no problem. But let's see if you know this formula. What can you say about absolute value of a plus b? It is less than what? I agree with this, but I'm amazed that students they don't know this formula. It's so basic. No, it's much easier than that. It's so easy. Yeah, I'm amazed that you're not able to say that. I agree with you. Isn't that obvious? What happens is that a plus b, if a and b have the same sign, then you get the same value. But the problem is that here they could subtract each other, right? But here they never subtract each other. They only add up. So it's obvious that this is greater. Okay, now I'm going to ask you a formula that is much easier. Yes. This morning they couldn't tell it. I agree with you. All right. Now here, what do we have? This is the absolute value of a sum of 2. Here is the absolute value of a sum of many. But it doesn't matter. If this works for 2, it works for 3, it works for many. So the absolute value of the sum is less than the sum of the absolute value. So it's less than the sum of the absolute values. You agree with this? Meanwhile, this is equal to also the sum of the product of the absolute values. All right. What can you say about this value? Okay, we know that x of n in absolute value is less than a for all n. For all n. All n. Yes, that was the obvious result, right? Don't let yourself disturb because of n minor k. It covers all numbers, so no matter what you put here, it's less than a. Now, suppose I write another sum. How, so we have two sums, this one is one. How do they compare to each other? How are they compared to each other? This is then like that. So this is like that. Isn't that obvious? All right. So y of n equals this, which is less than this, which is equal to this, which is less than this. Now I can factor out a here, right? And then what do I have here? B. Because we assume that this converge. I mean, this is k, but this is n, this is the dummy variables, right? So this is b, this is a. And I find y of n less than b times a. And this is true for any n. True for any n. So y of n is bounded. reaction. So S is stable. Why are you so silent? Okay, everybody followed every step, right? Okay, I believe that. Now, my question is as follows. Anybody is scared by this type of proof? Oh, you're not scared? Oh, you, only two, three, four. Yeah, because I know that whenever I teach this and I ask, some students, they honestly confess that they are scared by this proof. Why is it? You follow every step, right? But you are scared by the whole thing. Yeah? Even though you understand each step. Right? You are scared by the whole thing. Is that maybe because how could I have thought of doing it this way? Maybe that's the question?
So you're saying so many facts and all of a sudden they all go together.
Maybe what's happening is that you follow every step, so you say yes, 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 and in the end you get the result, and then you say yes, but I don't know why. Is that the feeling?
Yes.
But it does work, right? So you have the proof that this works, all right? Okay. So next we're going to prove the other one. Remember, the second one is harder, so that's why I teach second. So if you found the first proof hard, this one is going to be harder, even harder. Now we're going to prove the other direction. That means we're going to prove S stable implies that this converges. Again, we're going to prove the contrapositive. Contrapositive. Instead of showing this implies this, we're going to show that this diverges implies that this is unstable. Okay? So that was much easier to find the contrapositive. Again, we prove the contrapositive. So assume that this diverges. So diverges, meaning in this case it diverges if and only if it's plus infinity. Okay? Since we are adding positive numbers, when it diverges, it's automatically plus infinity. Prove that S is not stable. All right, so you know when they show movies on TV, sometimes there's a warning like PG-13 or some warning. So here there's going to be a sort of PG-13. That means you're going to be scared a bit, but I warn you in advance. I mean, if you're too sensitive, you can use it. All right, so I'm going to show you that. So I'm going to show that S is not stable. Again, to show that the system is not stable, you just need to provide one example, which is the nice thing, right? If I at the exam I say show that this is not stable, that is much easier than showing this is stable, because you just need to provide an example and pick the easiest as possible to make your life easy. All right. So here finding the counterexample is not easy, but here I'm going to give it to you. Okay. So just follow the steps. Okay. So take x of n equals 1 when g of minus n is positive, and minus 1 when g of minus n is negative. So don't ask me why I'm taking this, just take this. All right? Yes, take this. Is this a well-defined sequence? Yes, it's well-defined. I'm not telling you why I take it this way, but it is well-defined. Is it bounded? Absolutely. Okay? So far, no problem. It's well defined, it's bounded, and I can input it to the system and see what happens to the y of n. And you know what? I'm not even going to calculate y of n in general. I'm just going to calculate y of 0. So y of 0 is what? Is a sum of g of k, x of 0 minus k. Which is, of course, is x of minus k. Now, what is x of minus k? That's easy. You just replace n by minus k. What do you find? So you find, so x of minus k is, do you agree? Now, I'm not interested in x of minus k alone, but x of minus k times g of k. All right, so what do you get? You get g of k here, and minus g of k in this case. Okay, no problem. Now, can you give me an expression of this that is simpler? Okay, it cannot be g of k because I have minus here. It's much simpler than that. I'm amazed that students, they cannot answer this. It's fantastic. It's fantastic. It is fantastic. Yeah. Okay. I find amazing that you don't know this.
Something multiply like 8. Oh yeah.
What? He said that? Okay, I credit. I don't know your names. All right. So, isn't that obvious? No? No, you don't. Anybody who doesn't understand that? You? What is the absolute value of minus 2? This is A. This is A. This is A negative. The absolute value, this is what it's doing. It doesn't do anything when the number is positive. But it changed the sign when it's negative because it makes it positive. It changed its sign. Okay. Hello? All right. So this is what? This is absolute value of g of k. All right, so let me continue. So g of k times x of minus k is absolute value of g of k. Right? But we assume it's plus infinity. So this is plus infinity. Wow. I don't even need to see whether y of n is bounded or not. Y of 0 itself is already, it blows up its alone. So y of n not bounded. You see, this is a case where y of 0 is not even a number. Not bounded. S not stable. I'm done with the proof. Okay. Question. Who finds the second part of the proof even scarier? No, this second is just fine. Oh, good. Because this morning, yes? No. This morning, some students admitted that they found the second part even scarier than the first part. Anyway, what I said in the, okay, I give you a hint. I will not ask this proof at the exam. Okay. No, I will not. But the reason I wanted to show that proof is that first, we always want to justify why a property is true so that you can apply it. I will never force you to apply something that has no explanation. Second thing is that I wanted to open a window to give you the opportunity to give you an example of mathematics from the area of analysis. This type of approach is typical of analysis, but what you study mostly is algebra. That's why this type of math is a bit alien to you. But this is my favorite type of math. You know, mathematics is divided into algebra and analysis. It's two worlds, right? And this is the math I like. All right, now in this class what is important is not the proof, but is in, knowing how to apply this result. So again, this result is like helicopter one, is that when you want to figure the stability of a system, if it happens to be LTI, then there's a shortcut, helicopter shortcut. You just look at the impulse response, but this time the test is harder. You have to perform the summation of the impulse response in absolute value and see if it converges or not. So there's more work, all right, more calculus work. And again, if you use helicopter 2 when there's no helicopter, it will hurt you, all right? So, okay, so let's see. So this time, helicopter 1, I didn't give examples because it was too easy, but example for helicopter 2, I will give examples. So again, in every of my example, I will consider a system that is already LTI. Consider the LTI system of impulse response U of n. Is it stable? Is it unstable? Or not enough information? This time, you have to vote between 3 possible answers. Either you claim you claim that we can say it's stable, or you claim that the system is not stable, or you claim that there's not enough information to decide the stability. Ready to vote? Okay. Oops. You need more time? I give you 10 seconds. Okay, vote. How many of you claim this is stable? How many of you vote this is not stable? Okay, how many of you claim we are not given enough information? Okay. I'm not giving you the answer. I'm just going to use helicopter 2. All right. I can use it because it's given that it's LTI. So calculate the sum of U of n when n goes from minus infinity to plus infinity. So how much is that? Yeah, it's infinite. Yeah, it's not stable. You win. Look, it's infinite, right? It's if you don't agree, it's n going from 0 to plus infinity of 1, and that is infinite. All right, so not stable. So this time I give you an LTI system of impulse response alpha n U of n, and we are going to have the same 3 questions. Can you state is stable, or state is not stable, or not enough information? My eraser doesn't want to erase. All right, how many of you vote this is stable? 1. How many of you vote this is not stable? How many of you vote there's not enough information? Okay, when you say not enough information, what do you think so? It's negative. Yes.
So now we have enough information. That's what you're saying.
Okay. Okay, I make it negative. Let's vote again. I make it negative. Let's vote again. In this case, who votes this is stable? Who votes this is not stable? Who votes this? Who votes? You want to say stable? And who votes there is not enough information? So what do you want now? Decimal, I don't understand what that means. I only talk about real numbers.
What if alpha is super small?
All right. All right. The answer is not enough information. Negative or positive doesn't matter. All right. So let's calculate. So helicopter 2. Oh, yeah, I'm sorry. This one is not right. The circle was from before, no? All right, the software crashed, I think.
Did it really? Whoops.
Where is not stable?
All right, so helicopter 2, it says you want to calculate sum of this guy. Okay? This is impulse response. So this is equal to, do I need to perform the summation from minus infinity? No, I can start from 0. But when you start from 0, u of n is just 1, so you just have this. But this is also absolute value of alpha to the power of n, because again, a b is a b, right?
Yeah.
So I apply this n times, and I get this. Now, do you know when this is converging or not? It's called something, this is called geometric series. Don't tell me you never heard of that, because if you say that, that means you didn't do your homework. All right, so can you tell me when we know that this is converging or not? All right, hint. It's something you learned in Calculus 001. You must have learned this. This is converging if and only if.
I find one greater than one. That's the first is a less than one.
Less than, can you allow 1? Okay, so this converges, this is geometric series. This converges if and only if alpha less than 1. Okay, you're supposed to know that. It's the geometric series. Okay, you are supposed to know that from calculus. Here I'm going to write a mistake. Remember that sometimes I teach mistakes? So here a typical mistake is students who say that this converges if and only if converges if and only if alpha less than 1. So that is wrong, because then that means it converges for alpha equals minus 2 then. That is bad. I'm saying this because often students, they forget about negative numbers. This is not going to converge because absolute value of alpha is 2 in this case. All right, so the conclusion is that this system, this system is stable if and only if alpha less than 1 in absolute value. In fact, I should say in magnitude. All right, so every time, you know, my examples become harder and harder. So consider the LTI system of impulse response. N times alpha n u of n. So this is harder because n makes it more complicated, right? For example, if alpha is less than 1, this goes to 0, but n meanwhile goes to plus infinity. There's going to be a conflict. But there's a case that is easy to solve. So anyway, helicopter 2. Makes you calculate the sum of this in absolute value. Again, no need to sum from minus infinity. You can start from 0 and then you get this. And that is just this, right? Now, there's an easy case. When alpha is larger or equal to 1, anyway, this you know, when alpha is larger than 1, this blows up even without the n. So I write that this is larger than alpha the n going from 1 to plus infinity. I have to start from 1 because at 0 there's nothing here. Okay, so but we know this blows up. So in fact, this blows up even faster than this. So what I'm saying is that in this case, the system is even more unstable than the previous one. Okay, that's the clear situation. So S is not stable. Now the problem is when alpha is less than 1. So you want to look at this. Oh, sorry, mistake. All right, so now I have to return to this. Is that going to diverge or to converge? I propose okay, I'm going to propose 3 answers. Because of the n, it diverges, or it converges, or not enough information. Okay, so different. So here you have to see that there's a conflict. Alpha to the n goes to 0, n goes to plus infinity. All right, so 2 different tendencies. They are going to fight against each other. You understand that? So either one of them always wins, and depending on which one, it may always diverge or it may always converge, or there is a kind of not enough information. It depends on alpha. You know, think of it. When alpha is equal to 1, this is diverging, right? If alpha is equal to 1, this is diverging. Now, take alpha that is just slightly less than 1. Alpha to the n will eventually go to 0, but very slowly. You see, it's extremely close to 1, then alpha to the n will remain close to 1 for a long time, and then eventually go to 0, all right? So, but meanwhile, imagine that alpha to the n stays around 1 for a long time, but n in the meantime increases. You see that there's a kind of a fight of power. You understand? All right. Now you decide who is the winner, if there's a winner, or maybe there's no winner in the second case. So the first case is when you vote that n always wins. The last case is when alpha to the n is the one that is stronger. And in the middle is when you say, it depends on alpha. Ready to vote? Vote. How many of you vote that no matter what, this is going to diverge? How many of you vote? It depends. It depends on alpha. And how many of you vote that no matter what, it will converge? All right. Now, the delicate, when you say not enough information, that means you claim that it depends on alpha. That means if alpha is not too close to 1, then this may converge. But if alpha is too close to 1, so that means that there must be a threshold. So there must be a number, 1/2. So there must be a number. Then pi, no, it will not be pi. It has to be less than 1. Then it's going to be like a physical constant, right? Like a mathematical constant. All right, I give you the answer. You want to say something? Exponential? Yes. All right, so it's one of those things that I like in mathematics. Is like you have phenomena that is an analysis is full of surprises. Okay, before I return to this, I just want to digress a little bit. You know what is a cone, right? A cone. But imagine like a funnel. A funnel is like a cone reversed, right? But imagine a funnel that is infinitely long, and the tube goes infinitely small, but never zero, right? So if you follow the math, you calculate and you want to paint inside. You paint inside. If you follow the math, if you paint inside, it takes more paint than if you just fill the funnel with paint. Yes. Okay. If you calculate the area in the funnel, it is infinite. But if you calculate the volume, it is finite. So math is full of the surprises. All right, so here I want to return here, is that it doesn't matter how alpha may be close to 1. Alpha to the end will go to 0 in a much stronger way than A goes up. So the answer is that this always converges, always converge. Because exponential functions are stronger than, so the official math is to say polynomials. So the idea is that even if I put n squared, n cubed, like a polynomial, this is still stronger. So this is always converging, right? So conclusion, this system is stable if and only if alpha less than 1. So the n is not going to be of any disturbance. All right. This is the end of chapter 1.
Why?
Yes? Yes, because it's paragraph 9. You know, 1, 2, 3. It's the end of chapter 1. Okay. Is it good news or bad news?
It feels like it was chapter 10.
Is it good news or bad news? Bad news? Because you said that because you liked it. You like chapter 1, and you're afraid that the next chapter is not going to be as good, right?
What's that type of question?
Yes. Question.
Yeah, the last thing that we did, it converges to 0, right?
No. Not, the sum converges to a limit.
Limit, yeah.
Yeah. You cannot converge to 0. You're adding positive numbers. You cannot be. If you add positive numbers, you cannot.
Converging to some small number?
No, it converging to a limit. A limit. It does not blow up.
But we don't know what the limit is.
No, but we don't care because the helicopter 2 only requires that it converges.
Okay.
It's converging.
Okay, as long as we say converging to get 0.
Converging meaning it remains a finite number. All right?
So it's plus or equals to
Okay, you owe me something. So the reason I stopped the class earlier is because this morning I didn't go beyond this. I synchronized. And typically the second lecture I go faster because I'm more warmed up.